Let's review the concepts of pKa when we're talking about protic acids, so acids that have a proton to give away. pKa originates from measuring the concentration of H3O molecules, H3O plus molecules, when an acid is added to water. So essentially, how strong is this acid relative to water? So we can talk about a generic acid, HA. We add this to a water solution, so we say water is in excess. We assume this will exist in equilibrium. If HA is an acid, then it donates a proton, so we have on the right side of the equilibrium H3O plus and A minus. So here we have generic acid. Generic because there are a lot of different molecules that can act as acids, so we're just using a general HA here. We have water, and then these are the products when the acid dissociates in water. So with this equilibrium equation, or equilibrium reaction that we've drawn out here, we can calculate the Ka, so the equilibrium constant, we're talking about an acid, which is the concentration of products divided by concentration of reactants. Or in other words, the concentration of H3O plus, more specifically, and the conjugate base of the acid, so A minus, over the concentration of the associated acid with the hydrogen still bonded to the rest of the molecule. Now you'll notice we don't have water as part of this equation. Water is in large excess. Because it is the solvent. So for one, there is a lot of water there, and it would not change. The amount of water really wouldn't change any noticeable amount when we've added an acid to a solution with a lot of water. But also we're measuring concentration of each element relative to how much total liquid is there. So water is most of that liquid. So there's just a lot of water there. So we keep it out of the equation. So our Ka equation is the concentration of conjugate acid, H3O plus, conjugate base, A minus, divided by the concentration of the acid, the associated acid. And so if we have a strong acid, a strong acid is a molecule that's more willing to give up its hydrogen. Most of the molecules will have given up its hydrogen. If we have a stronger acid, then we're going to have a higher concentration of products. So more H3O plus and more A minus in solution. So higher concentration of products, higher Ka as a result, because we have a higher value in the numerator, concentration of H3O plus and A minus. So that's how we calculate Ka. It's a relationship between stronger acids, they have a higher Ka. Now, pKa is calculated by taking the log, which is base 10 of the Ka. Kas exist in really high, really large, and really small values, so taking the log of that value makes it more manageable to work with these numbers and a lot more straightforward to compare. So if this pKa is a negative log of Ka, that's also the negative log of concentration of products over concentration of reactants. It's abbreviated those words there. Because we take the negative log when we're taking the pKa, we take the negative log of the Ka, that means that very large Kas, so stronger acids, will have a more negative pKa. And then weaker acids with a smaller Ka value will have a higher pKa. So let's add this on here. Higher Ka, lower pKa. Again, that's because we take the negative log. That negative is important here. So let's look at some example values. Let's make a table of just Ka and pKa's. And then we'll look at some real molecules and what actual Ka and pKa values are. So if we have a Ka that's really small, let's say 10 to the negative 7, that's 0.00000001. If you take the negative log of that value, the pKa is 7. If we have 10 to the negative 4, so 0.0001, take the pKa of that, you have a pKa of 4. We have a value, a Ka of 3.26 times 10 to the negative 3. This is 0.00326, and its pKa is 2.49. You might notice that if we have a negative exponent in the scientific notation, then we have a positive pKa value. Again, that's because we changed the sign taking the negative log. Now let's look at a positive. So let's say we have a large Ka, 10 to the 3, or 1,000. A large Ka greater than 1, this has a pKa of negative 3. So lower pKa's are aligned with stronger acids. Higher Ka, lower pKa. Stronger acid, higher Ka, lower pKa. Let's look at some real molecules. So we'll write the acid name, we'll draw the structure too. We'll write the Ka of that acid and the pKa. Acetic acid is a carboxylic acid with an acetyl group. So a CH3COOH. This is provided on the pKa table that you will have for our class. But its Ka value is 1.76 times 10 to the negative 5. Its pKa is 4.75. Let's look at formic acid. Similar molecule. We have a carboxylic acid, but instead of a CH3 group, we have a hydrogen. Its Ka is 1.77 times 10 to the negative fourth, and its pKa is 3.45. So if you look at the Ka values, they are a magnitude of 10 different from each other. So acetic acid is 1.76 times 10 to the negative 5. Formic acid is 1.77 times 10 to the negative 4. Again, a power of 10 difference between these two. That correlates to the pKa's as one value different, 4.75, approximately 3.45. It's about one pKa value in between. So a small change in the pKa values correlates to a pretty large change in Ka values. But again, we use pKa because these are simpler values to work with. Working with something times 10 to the negative fifth or negative 4 or 3 or 3.26 times 10 to the negative 3, those are all large, either really large or really small values. And so being able to compare pKa's using pKa is simpler and more straightforward to work with.